So what is a queue? It's really just a line in which nodes or data enter and exit in a certain fashion. And let me show you how. So the first thing when you think about queues is to think of a line done in a supermarket, for example. So let's say we have the cashier right here and we have a line of customers. So I'm going to number the customers in increasing order. So the lower the number, the earlier the customer will be served. So 1, 2, 3, 4. Customer number 1 came first, 2 came second, and so on. So 1 comes to the cashier, and after paying for his products, he will leave. So I will erase 1 from the line, and so on. 2 will pay and leave, 3, and then 4. So what have we noticed? We have noticed that the first customer who enters, the first in, is going to be the first out, or first come, first serve, right? Now, the only difference between a queue and a stack, and we talked about stacks in previous lectures, is that it is the total opposite in terms of leaving, in terms of popping. We say pop in stacks. I'll introduce you to the terms just after I describe the difference between the queue and a stack. So if you've watched the videos, you could think of stacks as piles, and the first data that enters the stack is going to be stored at the bottom, and so on. We pile data on top of each other. So yeah, who's going to be the first one out of the pile? Of course, it's going to be the paper or data at the top of the pile, so 4. 4 is going to exit first, but here 4 is going to exit last in the queue, right? So what does that mean? It means that a stack is last in, first out, or first in, last out, right? Because the first one in was 1, and it's going to be the last one that pops out of the stack. So that's the only difference between a queue and a stack. Going back to queues, what do we call the operations of pushing and popping? So a push in a stack, which means adding or inserting an element, inserting X. The analog term of push in stacks is enqueue, which is also inserting a insert X, right? What is the analog term of popping in a stack? Pop means remove. Now we don't have to specify what we need to remove because the only thing we can remove is the paper on top of the stack or the data on top of the stack, which is here 4. We cannot remove 3 before 4. Right? Similarly, or the analog term of pop in stacks is dequeue in queues. So dequeue, right? Remove. And again, we cannot specify who to remove because it is clear that the one to be removed is the first one in the queue. So given this queue 2, 3, 4 in this order, 2 is going to be the first one served, then out it goes. Right? And I'm left with 3 and 4. So yeah, this is basically the difference between a queue and a stack. And those are the terms you should be using when talking about queues and stacks. Now, whether you're using queues or stacks, there's 2 basic implementations of both. So queue, do you want your queue to be of limited size or unlimited size? So when I say limited size means that you predefine the size. If you want a predefined size, you'd want to use an array because an array has a fixed size, right? So you can predefine the size of the array. If not, if you want the size to be unlimited and let the memory dynamically handle the size of the queue, then you'd want to use pointers, right? Now I know some people are going to tell me, oh, but arrays are pointers. Right? That's true, but when you declare an array in C++, you cannot do that other than allocating a fixed amount of memory to this array. Whereas pointers, you could link pointers to other pointers in an unlimited fashion, and you could free memory also dynamically. So we're going to be talking in this lecture using a predefined array. We're going to see how this is implemented on C++, and I'm going to leave the unlimited implementation till later on, after we at least introduce ourselves to linked lists. Now let's see how this is implemented on C++. So let's define a class called queue. And for a queue, we have to keep track of the front of the queue, pointing towards the first customer to be served, and the end of the queue. We should also keep track of the size of the queue, since we do not want it to exceed the capacity. Let's say I want a queue of size 10. So let me change the variable name size to current size, which makes more sense. And I would like an array of size, capacity. So those are the 4 basic and only properties you need to build a fixed size queue using an array. Now we need some methods. The constructor, we need to check if the queue is empty. It should return true or false. And we need to check if the queue is full. It's also a boolean. What else do we need? We need the 2 essential and most important methods, which are onqueue and dequeue. So if we want to onqueue, void onqueue, so we should add a certain value, right? So an int, and we need to dequeue, and we would like to return the value that we dequeued. And those are the fundamental methods you would need. So right here goes the properties, and down here goes the methods, where the first one is the constructor. Let's run to make sure everything is good. Okay, now let's build our methods. So the constructor, the first thing you'd want to do upon creating your queue, your empty queue, of course, it's empty, you're going to create an empty queue, is set all your properties. So your front could be set to 0, your back as well is set to 0 because no one is in the queue. Your current size is also 0, and the array is just an array. One more thing I'd like to add to the methods is print my queue. So I'd like to see at any given time what entries are in my queue. So this is my constructor. Let's write the isEmpty method. So bool, from the class queue, there is a method called isEmpty. I'd like to return true if current size is 0. If the current size is 0, then return true. Else, you would return false. Okay, now bool queue is full. So what should be the current size so that I say that my queue is full, otherwise it is empty? What should the current size be? It should be 10 in our case, right? So what we can do here is something, we can put the 10 here, but this would look really unprofessional, right? Because I'd have to change the capacity twice. Oh, no, so capacity. If current size is capacity, means my queue is full, means I cannot onqueue from it. Similarly, if my queue is empty, I cannot dequeue, okay? So those are the basic methods for the queue. Let's create a queue right here to make sure all is good. So I'm going to call my queue line. So let's check if the line is empty. It should be, or else I did something wrong. It is empty because 1 is printed. Now let's check if it's full. It shouldn't be full, or else I did something wrong. And as you can see, it's not full. Let me remove this. Everything is currently working properly. Now let's onqueue. Void queue onqueue int x. So I'd like to add x to my line. So before we start writing the onqueue function, I'd like to shed light on a very important point when implementing a queue using arrays. So let's say I have my capacity is set to 4 instead of 10, just for sake of argument, right here. And initially my size is 0, and both front and back point here. So it's not point as for pointers, it's just that the index is at 0, right? So F and B stand for front and back. And let me write the indices of the array right here, 0, 1, 2, 3. So when onqueue is called for the first time, this is what should happen. So let's say I called onqueue 5. So the following should happen. 5 should be inserted right here, and back should move to here, right? Because now back is the first empty entry is 1, right? So let me call onqueue 7, for example. 7 should be here, and back should move here. Good. Let's call onqueue one more time. I'm sorry if I'm boring you. That's why I put the capacity to 4. So now back is here. Let's say I call dequeue right here. So the following should happen. The front should be appended to here. Now, let me show you one last thing. If I call onqueue 15, for example, 15 should be added here. We shouldn't say that the array is empty before adding 15, because it's not empty. But where should back go? Should it point at somewhere, I don't know, which is index 4, which doesn't make any sense, points nowhere, this is back, or where should it point? Now, when using arrays, there's a very smart trick to that, and it is to bring back to the first entry, which is here, i.e. we set back to 0. Now, one might ask, but wait, how is back in front of front? It doesn't make any sense. Well, you should know that this is just for pointing, and the real list looks like this: 7, 10, then 15, and then 5. So this is my line, actually. If I want to write a function that says print my queue, it should print out this, okay? Now the queue is full, okay? And we should be able to see that from size, right? The size or the function, size is 4 now, so the function is full, should return true. Means that we cannot add any more data to the queue. So this point should be cleared out, and I think it's really important to know before implementing the onQueue function. So now going back to onQueue right here, let's write down the method. So first thing, we need to test if my line or my queue is not full. So is not full. If it is not full, then I could add X. So how do I do that? So A front is currently empty, and I should not use front, I should use back because I'm adding using the back. So A back should be equal to X, and I should append back. Right? Well, I shouldn't be doing that as direct as it looks. We should address the problem of this circular thing we talked about. So instead, we can do this. If back is currently capacity minus 1, then what you can do is bring back to 0, right? This is what we did when back was at 3. So when it was at 3 and we wanted to append an extra data, then we brought it back to 0, right? Else, if it's not capacity minus 1, just go ahead and append back as follows. And we shouldn't forget that we have a property here called current size. So since we added X to the queue, then we should also increment current size, right? And let's go ahead and throw a message saying the value X was or is onQueued, and down and full stop. So if it is not full, do this, and I do not want to continue the flow of the program, so I just return. If it is full, then we're at line 46. So let's throw a message saying the line or the queue is full. Try again later. Great. There's one small thing. Could we replace this block of code, this block of highlighted code, the thing that has to do with back of the circular notion? Could we replace it with a single line of code doing the same functionality? Well, yes, we could. And how do we do that? By using the modulo operator. So instead of doing this if-else thing, we can do this. Front is equal to front plus 1 modulo capacity. So let's give it a try here. Let's substitute it for some values. So when front is 0 and we run this code right here, what should it be? Now f is 0 plus 1 modulo 4, which is 1 modulo 4. So what is the remainder when we perform 1 divided by 4? It's 1, right? So 0 takes you to 1. Now 1 should take you to 2, and 2 should take you to 3, but 3 should take you back to 0. So 3 plus 1 modulo 4, i.e. 4 modulo 4. So what is the remainder when we divide 4 by 4? It's 0. And you could see that if I put here 4, 5, 6, it will repeat the same pattern. So 1, 2, 3, 0, 1, 2, 3, which really captures this round robin type of implementation. So instead of this block of code, let me just replace back is back plus 1 modulo capacity. Good. So this is how you onQueue a certain element X. Last but not least, how do we dequeue? So from the class queue, called dequeue, right? So instead of testing if it's full, now we have to test if it is not empty, because if it's empty, we cannot dequeue anything, right? So I'll type here cout the queue is empty and return something like -999, which is a number just to represent that we didn't dequeue anything due to an empty line or queue. Okay, so now if it is not empty, let's dequeue. How do we dequeue? All we have to do is append front to front plus 1, and also front should capture this circular notion. So we should apply the same thing as we did to back. Current size is now decreased by 1. Let's throw a message saying the value is dequeued. So which value should be dequeued now? So the value that you should dequeue, let's throw this here to avoid some confusion. So if we go back here, you could see that front points at the front. So this is what we should dequeue, right? Okay, so all you have to do is let's store this somewhere to avoid confusion. So let's store it in the value to be dequeued is equal to a front front. And let's print this and let's return it because this is what we want to return. Okay, it looks good. All the basic methods are implemented. Let us just implement print my queue to see how the queue looks like. So void queue print my queue. So how do we print it? Now if is empty, there's nothing to print, right? Let's just throw a message saying the queue is empty. Else we'd want to print the elements in the queue. So how do we do that? So assuming that back is in front of front, means no circular thing happened, you could just print from front to back. However, so you can do this. If front less than or equal to back, you could just run a for loop saying for int I is equal to front I strictly less than back, because back is empty, and I plus plus cout AI. And I don't want to skip a line because I want them to be printed next to each other with an arrow in between. Else, if front is greater than back, means that a circular operation has been done. Let's start by printing from front till the capacity. We can do this. I'll copy paste this because it's the same. And you could do another loop starting from 0 till less than back, because you'd want to start from 0 till back because back is less than front. And I plus plus cout AI, and there you go. So let's give this code a try. Let us run line dot on queue. Let's add 10. Run. The value 10 is on queue. Okay. Now line dot print my queue to test. 10 pointing to nothing means there's an empty thing. Great. Let's add some more stuff and keep in mind that the capacity here is 10. 10, 20. Let me print it now here. Okay. Let's do a dequeue and let's print the queue after the dequeue operation. So there's a small problem just from printing, not the code. Why is this sticking next to this? Oh, okay, because we did not insert an end L, right? So how do we do that? Just right here, cout end L, that's it. So run, there you have it. So this is this line right here that is highlighted. This line right here that is highlighted is the output of line 83. Then line.dequeue throws 10 has been dequeued, and then we print the queue again where 20 is the first element to be served. Let's add some more elements. 50, 60, 70, 80. Let's get rid of all this and let's just for int I equal to 1, I less than 100, I equals to I plus 10. Let me start from 0. So 0, 10, 20, and so forth. So each time this line dot onqueue I. Okay, run. So we've onqueued 1, 2, 3 up to 10 elements. Now let me throw a message. Test if my line is full. It should be full, and it is full. Now, can I unqueue one more time? No, I cannot. The queue is full. Try again later. Now, let me get rid of this. Let's dequeue once. So the first element has been dequeued, so my line should consist at this point out of the following elements: 10, 20, up till 90. So let's print to make sure. Print my queue, and there you have it. Now, the circular thing should happen. So when I come here and unqueue 100, what's going to happen is that 100 is placed in the beginning of the array, but at the end of the list. Again, 100 should be at the beginning of the array, but at the end of the list. So upon printing my queue, 100 is not shown for some reason. So the problem is here. This inequality should be strict. So you'd want to do this when front is strictly less than back, because when they're equal, there is a problem of printing nothing, which is what we saw. So this should be strict. So let's run this again, and there you have it. Now let's try to dequeue everything. So for int I is 0, I less than, let's say, 5. I don't know if we have 5. No, we have more. So 1, 2, 3, 4, 5, 6, 7, 8. Let me dequeue 7 at the moment. I plus plus and dequeue 7 elements. So print my queue, run. Exactly. We have 90 and 100 because 1, 2, 3, 4, 5, 6, 7 elements have been dequeued. Let's unqueue just for curiosity and print again. So I should be able to see 90, 100, and 110. Exactly. Let me dequeue again. I should be able to see only 110, right? Let me dequeue for the last time, for the last valid time, because I could dequeue as much as I want. I mean, run the function as much as I want. So there you have it. When I want to print my queue when it's empty, it tells me the queue is empty. And the value 110, the last value, has been dequeued thanks to this line. Let's try to dequeue one more time when it's empty. Does it tell me that it's empty? Yes, it does. It tells me that your line is empty. Okay, so just one small modification that we have to do before wrapping up queues. So if you go to the print function, you can see we have a lot of redundancy. So what I mean by redundancy is that we have like 3 for loops and an if-else statement only for printing. That's not nice. So it turns out we could replace all this code with only one cout and with only one loop instead of 3. So how do we do that? So let's first initialize our counter to be front, because as we can see I is front in both cases. Instead here is that because it's the continuation of the loop that precedes it. So initializing I to front first and using a do while loop while testing that I is not back, we could cout on AI, right, with an arrow. Perfect. And then instead of just adding I like this, so instead of I plus plus, we add I plus 1 modulo capacity, so that we bring I back to 0 when it's about to go to an index where it shouldn't be going to. Perfect. Run. And there you go. Okay, so in this video we talked about queues, basic notions and properties of queues, how they behave, the basic difference between queues and stacks. We also argued that queues could be implemented using arrays, as we did on C++, or they could be implemented using pointers for dynamic memory allocation when you do not want to predefine the capacity right here. I hope you enjoyed this lecture, and I'll see you then. Cheers.